So now let's talk about some computation laws of tensors. Well, plus and minus, that is adding and subtracting, I will not talk about, because these two we are all very familiar with, right? The adding and subtracting of tensors is just like the adding and subtracting of matrices. You just find the elements on the corresponding locations and you add them or subtract them respectively. That's all. So there's nothing to talk about. Okay, so let's talk about something that is a little more complicated, which is multiplication. We can say there are three kinds of multiplication between tensors. First and the second one are what we are, I think you are all familiar with, dot product and cross product, right? And there's a third one, I have mentioned it, which is the product where we do not write anything between the two tensors. That thing will be called dyadics. We'll talk about it soon. Let's first refer to the dot product. Let's consider the dot product of two vectors, A times B. We know that the vector, a vector can be written in the index notation, right? If we just use the unit orthogonal basis, EI. So EI times AI. Remember the Einstein's summation convention? Here we have the same index. So we need to sum the whole thing from I equals 0 to I equals 3. Okay, so this thing, dot the B vector, which is EJ times BJ. J can also go from 1 to 3. Well, there are two things worth mentioning. First, we see that the EI and AI here, between EI and AI, I didn't write anything, right? Do you agree? This thing is actually a kind of product. So this is a dyadics, right? So this is one thing. Also, we see that I used different indices for the vector A and the vector B, right? I used I and J. Why did I do that? Because A and B, those two vectors are independent, right? So I should not create a dependence by using the same index, right? So I use different indices. Okay. So we know that the AI and BJ are actually constants. So we can pull them out of the brackets, right? So this thing will become EI directly encounters with EJ, and then times AI BJ. So what's this thing? EI times EJ. We know EI and EJ are two vectors from the unit orthogonal basis, right? So this thing will equal to 1 if I is equal to J, but it will equal to 0 if I is not equal to J. Do you agree? Because if I is equal to J, then basically EJ equals EI. So they will be the same vector, right? Say E1 dot E1 or E2 dot E2 or E3 dot E3. So what will this yield? This will be the same vector squared, actually, right? So it will become 1. But what if I is not equal to J? When I is not equal to J, then those two vectors are different vectors. We also know that every two vectors in the unit orthogonal basis are orthogonal, right? So their dot product will be 0. So if I is not equal to J, then this thing will give us 0. There's a shorthand notation to write this. Let's define this thing to be delta Ij. Delta Ij. So next time you see EI dot EJ, you know that you can write it as delta Ij, right? Delta Ij just means when I equals J, this thing will give us 1. But if I is not equal to J, then this thing will give us 0. This is, you can say it's just a definition. It's called the Kronecker delta. Okay, so this thing becomes delta Ij AIBJ, right? So what's our next step? This thing will not always give us a contribution, right? Only when I equals j can this thing give us a contribution. So we only need to consider when I equals j, right? So when I equals j, then j equals I, and this thing becomes the delta ij will give us 1, and the bj here is actually bi. So this will give us aibi. Note that there are the same index here, right? So we need to sum this thing from I to 1 to I to 3. So what's the result here? If we write it out explicitly, it will be A1 B1 plus A2 B2 plus A3 B3, right? So from the index notation, this is the result we finally get. Does this is this result the same as our intuition, as what we have learned before? Yes, because A times B, let's say if we write it out as a coordinate form, then it will be A1, A2, A3 dot B1, B2, B3, the two vectors, right? So what will this give us? I think in high school we have learned that it will be A1, B1 plus A2, B2 plus A3, B3, which is the same as this. So actually, we seem to have taken a detour, but actually the merits of index notation we will see afterwards.